Okay, so now we're going to go into section 9.3, and we're going to actually build a simple transformer. And, really just on the two equations that we've looked at so far, we're going to base this elementary transformer on that. And just think about initially creating or inducing that voltage, and remembering that any coil that's in proximity of a magnetic field has a voltage induced in it. And so we're going to look at the effect of that. And this is the fundamental, the basic idea of how a transformer works. So this is figure 9.4 on page 185. And let's just kind of go through this right quick. Here is what we've been looking at before. Basically this section is what we've been looking at in relation to section 901 and 2. And so we have a coil, and it has a air core, meaning there's nothing inserted into it. And then it's connected to an AC source. Now we'll say this, and I'll keep harping on this throughout this whole discussion. These transformers do not work with a DC source. It has to be something that has change, because the rate of change of flux over time is how we induce a voltage in these. So it has to be something changing, like an AC source. And so once I connect this source to this coil, I get a magnetizing current, I sub M, and it produces a flux. Okay, so here's the flux that we create, and this flux is just dispersed out into space. And if we were to bring a second coil into proximity of the first coil, some of that are flux, and for an ideal transformer, we're going to say all of it does. Some of the flux that we'll just name this surrounds the second coil, and when that happens, varying flux around the proximity of a coil will induce a voltage. So that's what's happening here, right? There's really two coils at work, and one is connected to the source and induces a voltage, and that voltage that's induced creates flux, and that flux is used and put in proximity of the second coil and induces a second voltage that we call E sub 2. Okay, the coil that's connected to the source is called the primary, and the other coil where a voltage is induced by the primary is called the secondary. Okay, but the simplest way to remember that is that the primary is connected to the source, and that defines the primary side of transformer. And it doesn't matter if we're talking about a transformer that's used in small voltages, or if it's a transformer that's hanging on to a power pole outside with thousands of volts associated with it. Primary and secondary designations still apply. Now, we mentioned earlier that a transformer provides something called electrical isolation, and so let's begin to try to understand what that means. He tells us that there's a voltage that exists between terminals 1 and 2, and also between terminals 3 and 4. And he also tells us that there is no voltage that exists between terminals 1 and 3. Therefore, because of that, The secondary is electrically isolated from the primary. There's no difference in voltage. So that separation is what we term this isolation effect that occurs with transformer. If there was a varying different voltage across there, it'd be like any other voltage source, and there would be that attempt to supply current from one side to the other, but that's not the case here, right? These are not, there's no voltage that exists between 1 and 3, and that's where we get this concept of electrical isolation, and we will see that in some applications as we go forward and look at this in more depth. The next thing I want to point out to you is that the flux that's created by the primary, it can be broken up into 2 parts. You have what's called mutual flux, okay? Mutual flux, which is flux that links both coils, the primary and the secondary. And you also have something called leakage flux, which only is linked to the primary. Okay, so this would be the total flux produced, and then the components of the total flux, would be the leakage flux plus the mutual flux. Okay, and so what he tells us, and this is all in the construction of the transformer, if these 2 coils are very far apart, and because of that, not all of the flux produced is shared by the coils, only this part of it. And so we define a transformer by something called coupling, and we'll actually find a coupling coefficient that tells us how much of the total flux is coupled to the secondary and are mutually shared, you might say. And what we can do is we can bring these coils closer together. We can use different types of materials and cores to improve what is called the coupling factor. And we'll see this coupling coefficient that will be a characteristic of transformers, and we'll explore that. Then he goes on to say that we can improve this by actually some transformers, the primary and secondary windings are wound on top of each other, and that helps to improve the mutual flux, the share or the coupling that goes along with it. He says when the couplings are very weak, the secondary voltage, the E sub 2, is relatively small, and worse still, it collapses almost completely when a load's connected to the primary terminals. So, there's, just an understanding at this stage of how this transformer works and how can we improve on it. And that'll be part of what we look at as we go forward through this chapter 9 on transformers.